Let's take another look at this function that we've been dealing with in topic 1.9 and really address what we're going to start talking about next in topic 1.10. So let's take a look at f of x equal to, and again this is x plus 1 for all x less than 0. We defined it as equaling 3 for x equal to 0, and then we said it's x squared plus 1 for all x greater than 0. Well, the question that we're going to start asking in the next topic is going to be, is the function f of x continuous at x equals 0? Well, in order to really visualize this in terms of what we know right now about continuity, let's go ahead and draw a graph of this function again, just to remind ourselves of what this looks like. And what I have here is, again, the piecewise function. It behaves like the linear function x plus 1 for all negative values of x. So I'm going to be graphing a line segment here, or a line ray actually, that is going to have a y-intercept of 1, a slope of 1, but because it's x strictly less than 0, I'm going to have this open point right there at what would be the y-intercept, and so I have something that looks like that. Well, at x equals 0, I have defined my function as equaling 3, and so I have the point 0, 3 on my graph. And then for all positive values of x, my function is x squared plus 1, which is the parent function for quadratics, simply shifted up a unit, and so it looks something like that, and I can call that my graph of f of x. So the question is this function continuous at x equals 0? And right now you have a very limited definition of continuity that you probably picked up in algebra along the way. Somewhere you probably had somebody say to you, a function is continuous if you can draw it without picking up your pencil or your pen. And that is true, but we really want to give it a little bit more formal definition than that, and we'll do that with limits. So the question, is it continuous at x equals 0? Well, I have this line segment, but then I have this open point at x equals 0 where the function is 3, and then making my way back out of here, I have something that kind of repicks itself up here at 0, 1. But I can't draw this function because of this point up here in one single move without picking up my pen. So this function is not continuous. Now then, as I was doing that, I'm hoping that you're making some connections here with how we're going to tie limits into continuity. Here's what the issue was in terms of limits. That as I was approaching 0, my function was approaching 1. That's what we verified throughout this entire lesson. That as x was getting closer to 0, the function is getting close to 1. The problem here, and the reason why this function is not continuous, is because f of 0 is defined as equaling 3. So the question here is, let's say that f of 0 didn't equal 3. Let's say that we took f of 0 and brought it down here and said it was equal to 1. Well, all of a sudden, that now equals the limit as x approaches 0 of f of x. So let's say if this were true, and really this is me just taking this point and moving it down to 0, 0, 1. So if this were true, then would f of x be continuous at x equals 0? And the answer, if this point got moved down here and was essentially filling in this hole at 0, 1, the answer is yes, this function would be continuous at x equals 0. And it's this relationship right here that's really going to give us a formal definition of continuity as we start to look at that throughout the rest of Unit 1.